Okay. If I remember correctly, and stop me if I am wrong, we have not yet done this problem. Am I correct? Have we done this problem yet?
You're not screen sharing.
Oh, it must be a Tuesday. All right, have we done this problem yet? Do you have it in your notes? Okay, because I think the last ones that we were doing, I don't think so. Okay, I think the last ones we did had to do with the dividing the polynomials. And so I do still have several examples left that we didn't get to. And so that's what we'll do right now. Okay, so on this one, we're going to start with the methods that make sense to us. What makes sense to you to start this problem? What method would you depend on? Keaton.
I might try U substitution.
I think U substitution would be perfect. And we can see that there will be an issue with U substitution. Because when I take the derivative of U with respect to x, I just get 1. I don't get anything with an x in it like I have up here. So that means my du will be equal to dx. But it's still a good start. So we see here, we're going to have, I'm going to go ahead and bring that 2 out in front, because the constants, it's just easier to deal with them that way. And we have u squared du, but we can't take the integral until we get rid of all the x's. And so, do you remember the trick to get rid of that x that's still there?
You got me, dude. You got me.
Big yawn from Cormac. I understand.
I woke up at 6. I don't know why.
Oh, at least you were up. Alright, do you remember the trick to get rid of that x? Give you a hint, it has something to do with the u. Aurora.
Don't you take the u and then get x by itself and just math?
Yep, and we just math. Alright, so, and Annie, what you said in the chat, I'm not sure if this is what you meant or if you're meaning something a little different. But we do that right there. And so, now we can say that this is equal to, let's just go with the line. U minus 1 over u squared du. And at this point, I do have to keep modifying this. I'm not done yet. And that's one of the challenges you're going to have in this class is looking at a problem and figuring out how do I play with this just to make the integral work. Because right now, I can't do another u substitution. It wouldn't do me any good. But what I see, what it's very convenient, is there's only one term in the denominator. What that means is I could split these up and give each numerator its own denominator. And from there, if I do just a little bit of algebra, it makes it a lot easier to handle this derivative, or this integral. And then remember, this is where we're getting into the new topic. Anytime you're taking the integral, bless you, of u to the negative 1, or x to the negative 1, or 1 over x, or 1 over u, however you're looking at it, you get back out the natural log of that item. Here we can go back for the u to the negative 2, we go back to our old school rule, which is add 1 to the power, and then whatever that new number is, multiply it by 1 over that thing in front. And then the last step would be to plug back in what x is equal to. And again, kind of making my natural log look a little funky there at the end, just because there's so many straight lines in that problem. How'd that one feel? Thumbs up? Alright, good initiation back in on a new week and a new day. Alright, I think I've got about 3 or 4 problems left from the last lesson that we didn't get to, that we're going to keep going through. If any of the steps I do don't make sense to you, let me know as we go through them. But I will pause because I do know I go kind of fast, so I want to give you guys time to catch up. Okay. Now again, it's all about making a judgment call, and if what you try doesn't work, try something else. On this problem, I do recommend you substitution again. And I just want you to make a guess. What would you do as the u? Where's my Jeopardy music when I need it? That would be a possibility. We would want to have something where it would not be a direct change between the variables. So if we picked x to be the u, then it would change the letter, but it wouldn't change the format. We're looking to change the format. So we want more than just x in it. But that is a good guess. Very good guess. And for everybody else, that answer came from the chat. That's where I'm referencing. What makes sense to pick as the u? And honestly, we just have to try something. Let's give that a try. There we go in the chat. Alright, so by the way, I also would have accepted 1 over x, but you'll see where we're coming from that later. So, do you remember what the derivative of natural log of x is? This was all the way to the last lesson. I've already kind of referenced it once, but we took the integral instead of derivative. Look at your notes from last time. What is the derivative of a natural log of x? Okay, I got it in the chat from 2 of you. Now, in this problem, I can see I have the natural log of x, and I see I have an issue with an x. And it does turn out that actually does work for me very well, because what I'm going to do is I'm going to do a little bit of algebra. I'm going to go ahead and put my u in here, but then I'm not going to put in my du yet. What I could do, it would be a legal move to multiply both sides, or both top and bottom I should say, by 1 over x. Actually, let's just do this separate. Let's do 1 over xu, so I don't have to worry about the integral sign anywhere. And what happens is I multiply straight across, and on top I get 1 over x. On the bottom, my x's will cancel out because I have 1 on top, 1 on bottom within the denominator. So I just get that u. And so what's great about this is as I set up my du, my differential, I can see that differential working its way into the problem, even though it's not, the x is not in a place where I'm used to having it. So I have to do a little bit of tricky algebra first. But we get ourselves to a place where we recognize what that integral is. And that's what most of these problems will be, just playing with them. And I do mean playing with them. Playing with them and say, okay, I know these facts. Is there a way that I can make this look like what I already know? In legal ways. All right, and the integral of 1 over anything is going to be the natural log of that thing. And so this is a unique situation where our u was a natural log, so what we're doing is we're putting a natural log into another natural log. And since natural logs can be negative, you can't put negatives into them, but they themselves can have y values that are negative. Those ones will make absolute value signs like that. All right, some good initiations into the new week. Now let's do a little bit of trig. Now, my next few examples have to do with trig. There are some tricks I would expect you to be able to just see it and go for it. This is one of them. There are some where I'm going to expect that it maybe is going to be a little bit too difficult to remember the trick. And so I would say they'd be worth just looking up in the book after I show you why the trick works. But this one is one that I would expect you to be able to handle. Do you remember a trig identity to change tangent into other trig functions? What is tangent equal to in terms of other trig functions? Is your hand up, Cormac, or are you just stretching? Okay, Cormac, go ahead.
Yeah, my hand was up. Is sine over cosine, right?
Uh-huh. Tangent of x.
Or 1 over cotangent, but that's less important.
Yep, those are both facts, and that sine over cosine is going to be really helpful because with u substitution, what we're looking for in today's lesson is we're looking for something on the bottom and then the derivative of that thing showing up on the top. And so for today's lesson, the sine over cosine is going to be really, really helpful. And again, like I said, the thing on the bottom is what you want to take the derivative of, so that means that would be your u. Do you remember what the derivative of a cosine is?
Negative sign.
Yep. And I can see that I have part of that, but I don't have the negative sign, but that's a really easy fix. You can multiply both sides by -1, and there it goes. And anytime you see the integral of 1 over u, we get the same thing out of it every single time. What are we going to get here? Integral of u to the -1 power. You can tell me in the chat.
Natural log of u.
What is it?
Natural log of u.
It's the natural log of u. So anytime you see that you have, and what's going to happen when you're doing these integrals, because you're going to have the old integrals and these new integrals all mixed in together, you're just going to take the integral, and when you see that you get out a 1 over u situation, that's when you go, oh, that one was special. Which if you try the normal rule on it, the power rule, with adding 1 to the power and then putting that number 1 over that in front, you're going to see a problem. I just saw it in the log that is natural. You're going to see a problem, and then that should be your clue in that was the special one that's your natural log when that power rule breaks down. So this one's kind of weird too, because we're putting in, and you will need your absolute value here, we're putting in a trig function into our natural log. But that's okay. And if you want to get really fancy about it, remember we have the rule that says that if you have a power or a number out in front, you can multiply it in as a power. We could also say that this is the absolute value of 1 over cosine because it's got a -1 power. Let me put in the intermediate steps so you can see where I got that. Cosine to the negative. Actually, yeah, let's do it. That'd be tricky because with cosines, if I put the -1 up in front, it means something else. If I put it in the middle. And that means that I could say that I have the natural log of a secant, because 1 over cosine is the same thing as secant. And if I look in my front flap of my textbook, if you have your front flap of your textbook, go ahead and get that open because you're going to want it not just for right now, but for the next problem too. Number 8 down here, which you can't see that well, is your tangent. Put my finger on it, put it way up next to the camera. Whoa! Okay, so right there it is. And in the book, they choose to leave it in this form right here. Just because we usually like using the sines and cosines just a little bit more, I believe, is why they chose that one, instead of calling it the natural log of secant. I personally would have called it natural log of secant, though, and focused on that format. Alright, Andrea, thanks for letting me know. I am, hopefully, it's recording. I am recording this one. Yep. So I'll make sure that's up for you. Okay. How you feeling? Oh, cursive. That'd be a good idea. Yes, that's what I will start doing. I'll start doing the natural log in cursive, at least the L's, because that, I agree. I was trying to figure out a good way to format, and cursive would be a good way to do that. Thank you for the suggestion. Okay, so, no, again, how are you feeling? I've got a thumbs up, a couple thumbs, I've got like some hesitant thumbs up. I've got kind of a, okay, I want you to stretch. We gotta get ready for this next one. Everybody get a good stretch in. Because when you stretch, it opens up those veins and those capillaries and everything, and it gets the blood flowing, and we need that for the next problem. Make sure I'm in the right place. Okay. Now, how many of you have your textbook in front of you? Just wave at me if you've got it in front of you. Just a couple of you? Okay. If you have it, open to the front flap. We're going to prove to you number 10 in the integrals, the basic integral formulas. And for those of you that do not have your textbook in front of you, we'll give you a preview of what that is. Come on, there we go. Alright, Keaton, thanks for letting me know.
What's up, dude?
Number 10 says... Oh, let's remember. There we go. So we're going to prove to you why this is true. This is in the category of, I don't necessarily think that the trick here would be one that you would necessarily remember. Some people will, but it's not one that people would necessarily remember. I would expect you to more look this up. And I would also expect this probably... Now, it still could show up as a multiple choice question on the AP exam, but it would be one that they would like use once just to see if you remembered the rule, and that would be it. They wouldn't make a big deal out of this one if they used it at all. Now, if you think back to the rules of derivative, when is the AP test? It's the first week of May. Which, especially with spring break coming up too, I had to sit down with your textbook yesterday and think realistically, what are we going to have to skip? Because I don't want to just plow through material. That's why I'm checking with you guys. Like, please tell me if you're lost, because you get lost here, you're gonna be lost on the next things too. But this whole not having school on Fridays means that you guys have 1/5 lessons. 1 out of every 5 lessons I normally would have with my AP calculus class, you guys don't have, because 1 out of 5 classes we don't hold. So that is putting us behind schedule. Without that issue, we actually are doing better. We are doing very well, but that issue is pushing us back. So there are going to be things on the AP test that we will not cover because I'm making decisions about what you're going to see most of. So just as a heads up, because we don't see each other. I mean, my other option would be to make us have class on Fridays, but then that interferes with some other things like the office hours and the meetings I'm supposed to have. So there's no great solution to this year on that one. But we are hitting, by far, we're hitting all the important material. I am making sure of that. The ones you're going to see more than one question on, easily we're hitting all that. Anyway, some facts about secant that we should remember. If we take the derivative of a secant, remember that was equal to secant tangent. And this is going back to our rules from, we proved that one, I believe, using the quotient rule back like months ago now. And also remember the fact that when we took the derivative of a tangent, we got out secant squared. So on purpose, I'm picking the derivatives that gave us answers that were secant. Okay. So, the trick that will get us through is if we multiply our secant by a special form of the number 1. Remember that legally, that's really all we can ever do is multiply by the number 1. And we're going to pick on purpose the combination of these two. To define our number 1. And whatever we put on bottom, we have to put it on top too. And what I like about that, I see here in the next step, is I multiply the secant on the top, and I'm going to get secant squared plus secant tangent. What I like about that is what I see on top now is exactly what I got out of my derivatives. And that's the goal. When you pick your u, you want the derivatives to show up in the problem. And for what the problems we're doing now, you want to see them on the top. And so if I take the derivative of a secant and take the derivative of a tangent, I get back out these things. So, let's take u to be what's in the denominator. And let's take the derivative of each thing. And I see that whole big old thing. That becomes part of my differential for du. So I end up with just 1 over u du. And we keep seeing this 1 over u du over and over and over and over again. And when you see that, like the whole reason I'm going through so many of these is just to get you used to, oh look, we got a 1 over u again. What's that equal to? Hey, it's the same thing as last time. It's equal to the natural log of that u. Or in this case, the natural log of the absolute value of a secant of x plus a tangent of x plus c. Which, just for a quick little scroll, is what the book told us it would be. That's one that I don't necessarily expect you to remember the methods for. I wanted to show it to you to show you why it did work. But I personally would keep that front flap of your textbook handy so that on problems that you get stuck on, you can look at your textbook and say, what does this look like? And keep in mind, for the AP exam itself, you cannot have access to your textbook. But like I said, this is the sort of integral that I'll have to review the materials for the AP test, and all of you should have the Barron's textbook. We are going to be practicing that as we get closer to the test. But that in particular is an integral I don't expect you to see. I would expect maybe on a multiple choice without the calculator. Maybe one question, but that's really all I'd expect on the whole test, that you'd see that integral. Okay. I have, I believe, one more example from last time's lesson. And for this one, I just want to use the integral we just proved.
My intent was mainly, it'd be nice if it worked, mainly serve as an opportunity to observe how people are handling a potentially difficult situation, if it doesn't work, or what their processes are for figuring out a solution that nobody knows. So,
All right, we got a couple different things we can try. I just want to hear from you. Shout out what we could try. And remember, you can shout out in the chat. I've got that open in front of my face as well. And either Cormac's camera froze about 5 minutes ago, or he's really good at having a staring contest.
I'm just really good at standing still. My camera's not frozen.
Well, and that was pretty impressive because your mouth didn't even move when you said that.
I'm really good at ventriloquism too.
All right, so when you say change the square root first, what do you mean? This is in the chat that I'm responding to. Do you mean just change it to the power form? Yeah, okay. That is a good step. If you were to use a U substitution, what would you set U equal to?
So you reached out to Cisco, was that on their community support page?
Everybody's waiting for somebody else to respond. And it's also kind of funny, even though we're miles apart and we're on camera, to see how many of you are avoiding eye contact. Some of you are working this out, too. I do see some heads down as you're trying to figure this out. Do you want a hint? Would you like a hint? Okay, somebody said in the chat, if we're looking at this problem and we could say, we could try setting U equal to, like, 1 plus, I'm going to modify what you have slightly. I'm going to put the squared in there. And then when we try that, we have a chain rule situation, so you'd have 2 times tangent, so derivative of the outside, and then the derivative of the tangent, or the derivative of the inside, would be a secant squared. And so my primary issue with that is we don't see this stuff, but personally that's what I was hoping that you would say. I was hoping that you would say, we've been doing all these U substitution problems, let's try this. Because realistically, when you don't have the teacher here in front of you, you're going to be on your own and you're going to just have to test things out. And then make the judgment call. And I wanted to say, like, let's talk together. Make the judgment call of, do we see this in the problem? And if we don't, then it's just time to move on to another method. And this was a really great one because we've been so focused on use substitution. This is going to, the best way to go about this one, and maybe the only way, because I personally, even with my experience, I can't see another way to solve this problem. We probably should use a trig identity first. And if you have your book, turn that flap to, from the integrals and derivatives, just turn the page to the trigonometry. And there is a trig identity that uses 1 plus tangent squared. And it is important that that tangent is squared. It won't work without it.
Yeah, when I saw you go into the server room, I've got all the in tomorrow. I have a full knowledge.
And if you don't have your book in front of you, you can always Google trig identities. Look for one that uses 1 plus tangent squared.
Have you done much with sorting through, like looking through event logs to identify issues?
All right, there we go. So, got it in the chat. 1 plus tangent squared is the same thing as a secant squared. It is a trig identity. It's true no matter what angles you plug in. Those two are the same as one another. So what you can do as a legal move is you can take what's inside those parentheses here and replace it with a secant squared. And very conveniently, this means we're taking the square root of something that's squared. What happens there when you take the square root of something squared? That's right.
Cancels.
They cancel. So we end up, before we even touch the calculus, we can play with this in a way that makes the integral possible. And that right there is, by the way, the challenge of integrals, is you have to play with them more ahead of time and try to figure out the right way to play with them. And you're going to try something and it's not going to work, and that's okay. Try it, go as far as you can, and then say, okay, well now let's try something else. You will have to do that more with integrals than you had to do with derivatives. Derivatives was just take it. That's all you got to do. You just take it. You have these rules, and you just have to keep the rules straight. This one, integrals will require sometimes more playing with them to say, okay, I've never taken this one before, but I have rules where I can change this so it looks like this, and now I've taken the integral of this before. And very conveniently, I'm going to scroll for a second, the integral of a secant is exactly what we did in the last problem. It's going to equal this big old thing, and so instead of proving it again, I'm just going to use it.
I don't know on that. Yeah, 'cause we need to get something sorted out for that. It might just be that I spin up a new VM and replicate the software on this for tests. But
And let me tell you, even though I've been doing calculus since slightly before you were born, which is always so weird to say, this is an example of a problem that I couldn't do without grabbing a book and a reference sheet, because I don't have the integral of secant memorized. I have played with trig identities enough. I am a little more comfortable with that piece, and it just takes playing with them the more time you spend with them, the more comfortable you are. And we've already had the discussion this year about how, because of math situations last year, only really the students, very few of the students who were at Ames last year feel comfortable with these, I know. Now, we're not done yet because we do have to plug our numbers in. So we're going to take the natural log of, we have to plug in our pi over 4 first.
Sorry about the tries here in the background.
And then we plug in our 0.
I'll review myself. Give me just a second.
And then you can maybe hear my poor crying baby in the background. My husband's, your class is the one he tends to take the baby for because we've got so much to cover. So if he, unless he's in a meeting, he takes the baby so you guys can get a little more of my attention. And when you plug angles into trig functions, you've got to have the unit circle in the back of your mind. So a secant, remember, is the same thing as 1 over a cosine. For me personally, it's the cosines that I can remember. Your pi over 4 on the unit circle was the same thing as a 45-degree angle. And the special triangle for a pi over 4 was your 1 square root of 2. I'm going through and just showing you in my mind, this is how I organize my thoughts on this problem. Just because I don't have like a visual memory where I can just think of what the unit circle looks like exactly in my head and have everything memorized. I have to kind of work through that process of, okay, what was the special triangle that goes with the situation, and then I take the cosine of that triangle. The cosine of this is going to be your adjacent over your hypotenuse. So this would be the same thing as 1 over the square root of 2. Do you follow where I'm going with that? And then the tangent of that one I can just take the tangent of my triangle directly. That's going to be the opposite over the adjacent. And so I can come up here and say this was 1 over the square root of 2, and this was 1 over 1. And before I finish, I am going to go ahead and do the 0. Here's your 0. Your secant of 0 is the same thing as 1 over a cosine of 0. The cosine of 0, if you remember correctly, and this one, again, we haven't done trig for a little while in this class, the cosine of 0 is 1. And the tangent of 0, let's see, that would be your opposite side would be 0 over 1. Your tangent of 0 would be 0 over 1, or 0. So I can finish off my problem here. I've got 1 over 1, and I've got 0. And I got a lot of stuff down here. Okay. I use the rule about my teacher's sister whenever I'm dividing a fraction by a fraction. Let's not bother with 1 over 1. Let's just call that 1. Minus the natural log of 1. I end up with the natural log of the square root of 2 plus 1. And so many rules. I respect it. So many rules to keep track of. The natural log of 1 is 0. So that whole thing goes away. And let's see, I don't even need the absolute value because this is already a positive number. So I started with integral of 1 plus tangent square root of x to the 1/2 power. I get that out. There is no way I could have looked at that problem from the beginning and go, oh, I know that's what the answer is. It just does take some playing with it. And you remember that whole big conversation I had with you first quarter about you got to be brave and just try it? Integrals are definitely going to be the same sort of thing, especially as we learn more and more of them. And that's one reason why. I cannot stress it enough. This front flap on your book and second flap for trig identities, have that handy for the rest of the year. Have that handy so that you don't have to get caught up in the what was this integral. You can look at the book and say, what does this feel like? What does this look the most like? Can I use the rule that it's in front of me? All right. Time for another stretch break. Everybody, I want you to stretch. I want you to think about puppies and kittens while I get my notes set up for the next lesson, because we are going to quickly go through the next section. I did think about not doing it to you and being nice to you and just finishing the last lesson, but when I looked at how many days we have left before the AP test, I realized I can't. And so that's why I am going to stress you out a little more. Let's see, I think it's this one.
The users will typically connect and then disconnect their sessions, leaving their apps open,
Can't open this file.
which will keep Windows updated.
That's no good. Give me an extra second. There we go. Luckily, because I knew we were going to spend enough time on the other stuff, I kept this purposely short. And I just picked out the most important information for you. All right. Did you get a good stretch in? Did you visualize puppies and kittens while you did it?
Yes, between the 6th and yesterday when I restarted it.
A little yes, a little All right.
It was in the morning.
This section, more than anything, is really to set up what's coming next, but it is in and of itself still a very important section. The whole idea with section 5.3 in the book is it's talking about inverse functions. And most of the section focuses on the algebra of what is an inverse function, and I'm going to touch on that, but I'm going to get pretty quickly into the derivatives, which honestly was just the last little bit of the lesson. But before I do that, like I said, I do want to do a little bit of the algebra. So first of all, I want to point out, you guys are used to inverses. These aren't inverse functions, but these are inverse operations. Inverses undo your original. If I was subtracting, I now add. If I was multiplying, I now divide. And every function, to my knowledge, has an inverse. Now, the inverse is not always a function itself, but we'll get into that in today's lesson. But there is always an inverse to whatever you do. Now, when I talk about functions, here's an example of inverse functions. And do you remember the process to find the inverse function yourself? See some head nods? What was the process? What do I have to do, say, to the f of x to get g of x?
You gotta switch the x's and the y's, so like x becomes y and y becomes x, and then you gotta get y all by itself.
Perfect. Switch your x's and your y's, and then solve for y. Oops, equals, there we go. And we can see that's what we have over here. Now, there is a property of inverses that I don't know if you studied last year or not, that will be helpful for you. Sorry. We have somebody in the waiting room named Do any of you know who could be? I don't let in people if I don't recognize them, but I know like Lala was supposed to come late. It sounded like. Give me a second to take care of them, just in case this is somebody in our class. Okay, so here is the rule that I do not know if you learned before. We should say if you take the composite function, in other words, you plug your g function into your f function, or your f function into your g function. If you get out something very specific, these two functions were inverses. And that thing that's very specific is if you get out exactly x, then f and g are inverses of each other. Did you learn that last year? Seeing some no? I didn't think so. But this is a helpful trick. If you're just given two functions and you're told, can you tell if these are inverses of each other or not? All you have to do is take a composite of them and see if you get out exactly x. Now, not a negative x, not a 2x. It has to be exactly x. If you simplify it and you get exactly x, they were inverses of each other. So for these two functions that I have here, that means that we would say take f of g of x would look like, you remember you write the f function, but where the x is, you leave a space. And where the x was, you plug in the thing inside the parentheses. We plug in the g of x. And then you do your algebra to solve it. I see I've got 2 divided by 2. I can give my 2 outside legs so I can see one's on top, one's on bottom. They're going to cancel. And I get x minus 1 plus 1, and I can see minus 1 plus 1. Those are going to cancel, and I get out exactly x. And I could also take the g of the f, in other words, take my g function, leave a space where the x was, and plug my f function into that space. And it should not matter what order you go in. Either way, the composite function should equal your x. So I do have some problems I'm going to give you to practice with today where you just say, are they inverses of each other? And there is one other way to tell if two functions are inverses of each other. It's not as exact, but it's a really good visual. And this one I do expect that you probably did learn last year. Andrea, would you text Lala and just check and see if she's trying to get in? I know we're missing a lot of people, so this that's sitting here in my waiting room, I don't know if it's supposed to be a me, but they haven't emailed me yet, so. And Sathya, yes, I just fixed it. That was an X. So I feel like we did teach you this with logarithms and exponentials. If we take a mirror and we put it on the line y equals x, we could maybe have an exponential function, and we could have a logarithmic function, y equals a to the x, y equals the log base a to the x, and those are inverse functions of each other. And something that's convenient about that is if there's a point, I hate to use a twice, let's use we'll use like c comma d. If there's a point c, d on one of the graphs, then it's a guarantee that the point d comma c, the switching of the x and y, will show up on the other graph. Okay, Andrea, thank you. And that fact right there, we're definitely going to use in today's lesson. skip over a little bit and probably come back to it. And like I said, I skipped a lot of material in this book to get right to the derivatives. So I'm going to give you the rule for derivatives of inverses. It's one that I recommend that you have handy in your notes where you can find it. Not just for the next week, but for, say, like the next month or so. If you have a cheat sheet that you've been putting together for the test, put it on the cheat sheet. Because like I said, if you have a cheat sheet, just hold on to that. From test to test to test. And just add to it as we go. So you don't have to recreate it every time. Are you ready for me to move on? Wave at me if you're ready for me to move on. Okay. I don't have quite everybody. There we go. Thank you, EJ. And then Cormac there, just still in his staring contest. I am recording this and I will put it up after class. So if you need to go back through any of the examples today, you can. Okay. All right, Jared, is that you as the We'll find out. I got an email from Jared saying I wasn't letting him in, so I'm guessing this is him. There we go. Jared, is that you? Jared Weeks? We'll see later. Okay. Alright, so this right here is how we're going to write the derivative of an inverse. And of course, when you see this, this is the inverse function. And this condition is given just because we can't divide by 0. And so since we have that on the bottom of our fraction, it's just there as a condition of just a reminder if this equals 0, it doesn't work because it can't divide by 0. So I think it's just 2 examples. Yeah, just 2 examples and then we're going to be done. And just to show you how we're going to use this. Cormac, yes. All right. So, you have a couple of ways you can think about this with inverses. First question is asked is find the value of our inverse function at x equals 3. So in other words, A is asking find inverse of 3. For me personally, and you might be different, but for me personally, I like to use the ideas of tables because for me personally, when I'm thinking about individual points, those tables are the most helpful. So what I'm looking at is a situation where I plug 3 in for my x and I'm asking you what do I get out for the y. But I don't have the inverse function, and quite frankly, I'm not even sure what the inverse function itself would be. Because I can switch my x and my y's, but how do I solve for y when I've got a y cubed and a plus y in the problem? The quadratic formula doesn't work because it's a cubed. It's not that it's impossible, but it's probably complicated enough that I don't know what it is. And again, my first time in calculus was in the year 2001. I've been doing this for a little while, and this isn't even a calculus issue. I've been doing algebra even longer, and I have trouble looking at that and figuring out how to use that rule of just switch your x and y's and solve for y on a problem like this. So this idea of the table is helpful for me because I know that means that I also am going to have some original function, which I do have access to. And that means, remember with inverses, you switch the x and the y. So that means that my original function is going to have a place where the y value is 3. And I want to know what x value gives me a y value equal to 3. Do you remember doing this with inverse functions last year or the year before? And just be honest. Like, you can say no. Yeah, okay. And that's fine. So what happens is I can remember even I was using this because I can remember teaching it, but just because I taught it doesn't mean we always remember it. Goodness knows you learned more than one thing last year. So the whole idea with inverses is it's a switching of the x and the y. You can switch x and y on the graph. You can switch x and y in the table. You can switch x and y in the equation. It's always a switching of x and y. So I'm going to use that to my advantage with the graph. And give me a quick second to get the graph over here. I'm going to graph the function and I can see if I were to put a mirror up at the line y equals x, I know I could graph that function pretty easily. It's more finding the equation for what that function would be that really would be the difficult thing. So I know that on my original function, I'm looking for a y value of 3. And I love Desmos for this. I can put in y equals 3 and right there it spits it out for me where those intersect. And it tells me that for this function, I'm going to get x equals 2 will give me y equals 3. Again, I'm using lots of pieces of math together, and if they get jumbled in your head, I understand that. But I use the graph to help me find what the x value is because algebraically, if I were to come and just try to plug in 3 equals 1 over 4 x to the third plus x minus 1, the first step's not so bad. But then after that, it gets kind of ugly. And, I mean, I would probably move that 4 back over to this side. But what rules do you know that allow you to solve a cubic? We have plenty of rules for quadratics, but cubics are just awful, awful, awful. And so that's where I personally, if I get stuck, I use the graph. And I say, I do know something about the graph, and the graph tells me that this should be a 2. Which means this is a 2. So, the value of my inverse when x equals 3 is 2. Using the original function and its graph, it helps me to find what the y value would be for the inverse. And for the derivative, we're going to use this new rule. That says take the derivative of the original function and then plug the inverse into it. So I can handle it. I can take the derivative of the function that I was given. Let me write that up again. You have it in your notes, but I know it's not on the screen. This is very easy to take its derivative, but I can't take the derivative of its inverse if I can't find the equation for the inverse. But what's neat about this is you actually can find the derivative even if you can't find the equation. We find the derivative, and we want to know the derivative of the inverse at 3. So what that means is I take my answer from up above and I plug it into my function. There's a lot of pieces here to be keeping track of. And I only planned for 2 examples, and realistically I only have 3 minutes of class left. I can do the second one for you. But I can tell you this example is also in your textbook if you want to play with it there. There definitely will be a problem like this on the AP test. This is actually a pretty big rule, even though I'm not spending a sufficient amount of time on it today. This is a pretty big rule for calculus, and this is going to be most helpful to find the slope at a very specific point. So all I need to do now is I simplify this. And this tells me the inverse function has a slope of 1/4. Oops, sorry. Of 1/4 at x equals 3. And notice if I plug in the number that's paired with the 3, the 2, into my original function, what happens here is when you switch your x and your y as you go between your inverse function and your original, your slopes flip. There's this relationship between the two that mathematically writing it out looks crazy complicated, and it will take some getting used to. But there's this relationship here that's really special between a function of its and its inverse. And I will touch on it a little bit next class, but we're really going to do next class is we're going to use it to find the derivatives of the inverse of the natural log. And what is the inverse of a natural log? I think you gave it to me in sign language, Aurora. But I don't remember my sign language well enough. The inverse of a natural log uses the natural number. Okay, that last piece, I know that the example might get you. When you get to those homework, I think I gave you 4 or 5 problems in your homework that use this rule, and I do have one more example that that I will tell you what I'll do is this video I'm making, I'll just tack it on to the end of that. Alright, good job making it through today's lesson. That was a whole lot. So this next problem that I've got prepared for you actually is one of your homework problems exactly. So it will be interesting to me to see who actually decides to watch the end of this video, because I am doing this work for you. So in this problem, this is problem 71 from your homework, we are being asked to find the derivative of our inverse function at some specific x value, that x value is a. For our equation is f of x equals x to the third plus 2x minus 1, and our a value is 2, or in other words the x value that I'm going to plug in. So in this example, this is another one where if you are trying to use our algebra methods to switch your x and y and solve for y, it's going to be not just difficult, but maybe even impossible to find the equation that's going to match, just because we have that cubic in here again. The cube functions, we don't have the same rules as with quadratics. So this is another one where I would turn to the graph to help me understand what that derivative should look like. So there we've got our last problem pulled up. Let's get this switched around now so that we're going to look instead at f of x is equal to x to the third plus 2x minus 1. So it's a pretty simple function, but the equation for the inverse just is going to be awful to try to find. And we know that we're plugging this a value into the inverse. So this a value here, this is the x value for the inverse function, which means it's the y value for your original function. This is what I was trying to get across when I was talking about switching your x and y's, and I was using the table format. So since it's the y value for our original function, let's plug in y equals 2 to find out where those two cross. Because this is just going to be a lot easier than trying to solve it algebraically. Just go right to the graph. It's actually, this is often the easiest way to solve equations, is to use these sort of tricks with the graph. But we teach you so heavily on the algebra because it's the harder method that a lot of times students forget that we can even do this, or don't even know that we can do this. So what I see here is when I want the y value of 2, it takes an x value of 1 for the original function. So if I were to make a table of the original function, I have the point 1, 2 shows up on it. For my inverse function table, we switch the x's and the y's. So I know, therefore, that the inverse function at 2 is equal to 1. And I need that for the derivative that we're going to take. I also need to know what the derivative of my function is. And we can find that pretty easily. Even if we can't find what the function is going to equal, we can find its the derivative of the original and use the rule then to put this all together. So, as a reminder, the rule says that the derivative of an inverse is going to equal 1 over the derivative of the original with the inverse plugged in as a composite function. So what we have here is this will equal 1 over my derivative, so 3, and I'm going to leave a space where the x was, and then I'm going to plug in this case it's the 2 that I want to plug in. I'm going to plug in what it equals, which is just 1. Do you see where that came from? I mean, there are so many pieces here, and trying to keep them straight, I totally understand where this is confusing. And I don't have time to do more examples for you right now, but I will try to tack some examples onto this before I post it to YouTube. Anyway, you do then need to simplify this out, and we get that 1 over 5 is the slope of your inverse function at x equals 2. And this also means that 5 is the slope of your original function at x equals 1. It might be easier for you to find the slope of your original function at the x equals 1 and then just flip it upside down for the other one. Anyway, we'll pause there. I'll see if I can do some more examples for you before I post this. And if not, then apologies, but I'll post it with this example.